All right, good morning and good afternoon, everybody, depending on where you're joining from. Thank you for joining us today for a webinar on INFINAM TPC. This is a brand new elastomeric solution from Evonik and validated by the Nexa 3D team on our QLS platforms. And we're really excited to talk to you guys about what makes this material so different from other TPEs and TPUs you might have encountered before, both in the SLS and in the resin world. I'm going to give it just a few more seconds for everyone to join. And with that, we will go ahead and get started. All right, so today's topic is obviously TPC. So we want to make sure that you understand what makes TPC different, how you can use it in terms of certain applications or use cases. Certainly want to make sure you understand the performance characteristics of TPC, and also a unique feature of any sort of elastomeric material, but certainly something that we see that's quite a positive result of utilizing TPC is how you can control the performance or feel of that material through design. And we'll talk about that both from a technical perspective as well as a customer use case as well, so that you can understand that too. Lastly, as we look at any sort of elastomeric material that's production worthy, if you will, something you can actually use for in-use parts, you start to think about scalability. And so we'll also quickly review how you can automate your production workflow for TPC components to ensure maximum throughput. And lastly, how can TPC impact those production parts, including footwear and sporting goods? I don't know if you saw any of our social posts or anything like that from Formnext or our announcement. But we've got some great examples of footwear and sporting goods designs as well that you can see utilizing this TPC material. So if you're not familiar with Nexa, just wanted to give you a brief overview. So Nexa is headquartered in Ventura, California. We were founded back in 2016, so we've been around for a bit. And we hold technologies in both resin and thermoplastic printing processes, and have recently added metal printing capabilities with our QLS platform as well, and announced our intent to acquire Syntium 4 filament as well. So quickly rounding out our ultra-fast 3D printing production capabilities. While we are new, we are robust. So as you can see, we have well over 100 partners across the globe, with over 1,200 printers installed worldwide as well. And probably a hallmark of our technology is that these are all open source platforms, meaning you can utilize our materials if you'd like. We have almost over 40 validated materials for our resin and thermoplastic printers, or you can use your own as well. We understand that materials drive applications, and that's why we invest in materials like TPC each and every day. But certainly if one of those materials don't meet your needs, we don't want to be that to be a limiting factor for you. Next slide. But what brings us to work every day, and certainly an exciting kind of component of the TPC conversation today as well, is building a sustainable digital supply chain through additive manufacturing. It's something that we're all passionate about here at Nexa, and it's something that we keep in mind as we look at both material validations as well as our technology and what we can do with it. So I will be finishing up my portion of the speaking today. I want to quickly introduce our speakers. So we have John Calhoun, who's our director of QLS Business. John has been in the industry for a number of years and brings a lot of expertise regarding powder bed fusion technologies, and certainly on the material side. That's where a lot of my experience comes in as well. And I don't think we have been more excited about an elastomeric material, John, until we found TPC. So you'll see, hopefully our enthusiasm is conveyed throughout the presentation today. And joining us as well is Dwayne from La La Land Design and Production House. So Dwayne comes to us with a ton of experience in leveraging design for the footwear industry, as well as some other products as well. And he has had his hands-on experience with TPC. He's been in the mud with us, really learning how to leverage this material to the best of its ability, and really kind of shaping that conversation I talked about a moment ago, which was how can you leverage design to affect the performance of this material? So John will talk about TPC and all the great things about that material, from a high level, and then we'll turn it over to Dwayne, who will kind of give his first-person user experience of TPC material, how it relates to other TPUs or TPEs he's leveraged in the past, and what he's excited about in regards to the future of TPC. And with that, I will turn it over to John. Thank you.
Yeah, thanks, Lewis. I appreciate the introduction. So here today, we're going to focus primarily on TPC for the footwear industry. However, this material is so robust and so unique that there are many different industries that can utilize a robust elastomeric material with these type of mechanical properties, which we just haven't seen in the industry. Of course, Nexa 3D offers a high build volume, high speed SLS printer, the QLS 820 for the production side of this. We also offer the smaller QLS 230 and 260 for doing smaller pieces, maybe something smaller than midsoles or other type of sportswear um, parts. One thing I want to focus on here is there's a lot made of Shore A durometers of materials, and I think it's important to understand a change that's happening in the industry of people starting to understand how meshing your geometry can affect the net shore rating of a material. And while TPC has a Shore A of 95, it's so durable, it will allow you to generate a mesh like I have on the screen here with a 1 millimeter strut diameter that gives you a net shore rating in the 40s. So these things kind of work hand in hand. If you want to be able to have a soft, pliable, low shore material via mesh, it also has to have the resiliency, the toughness, and the rebound to stay together and stay in one piece as you start to flex that mesh to give you the low shore rating. And TPC certainly excels at that. And that can be seen in footwear, orthotics, prosthesis, other applications as well. But today, again, we'll focus on TPC and sporting goods. Those of you who were lucky enough to join us at FormNext got a chance to see these shoes that we made in conjunction with our partners, which we'll talk about later in this presentation. And this was just an idea we had at Nexa to put together a great example for TPC, and we were able to complete this entire project and make about 10 sets of shoes in under 3 weeks. And I think that's absolutely unprecedented, certainly if you start thinking about what goes into making footwear with traditional manufacturing, molding of EVA foams and things like that. But if you just think about shoes, there's tons of components that go into shoes. And many of these would be excellent applications for TPC based on its durability, its low cost of manufacturing, and customization across many sizes. The thing that gets lost on people sometimes is you think about making shoes. Well, it's not just making one style, it's making, 22 sizes or more of a shoe in men's and women's, and then all of these internal components. That's a lot of tooling required to make a line of shoes. What we're bringing to the industry with materials like TPC is now the ability to do customized pieces and customized shoes on demand, which is really unprecedented. And that really just comes down to having the right elastomeric material with the right durability, the right softness, the right capability in the print side that would allow you to get into colors and dyeing and all of these things we'll talk about today. So again, you can see the piece of the midsole we produce with TPC for FormNext. What you can see on the slide now is the actual 820 running a whole range of parts in TPC. You'll notice this material is white. When the parts are finished, they are bright white. that allows us to dye the parts any color. Here are some examples of how this dyeing can be done. It's very, very easy to do. You can use a heated bath, as I've shown here on the left, just basically heating up your water to around 200 Fahrenheit, adding the synthetic grit dye, dropping your parts in. The longevity of the dip will determine the intensity of the color, but you can even go easier than that. I actually did some parts on the right here just using tap water. So no heat, just using, warm water from the tap and using the synthetic grit dye that you can pick up at your local craft store. You can get pretty inventive with dyeing scenarios and fading these type of midsoles or any other product that you want to create with TPC in this way. So you can go as far as you want with automation, which we'll talk about, or you can do it as minimal as your budget will allow. At the production stage, clearly the 820 with its 4 laser system and the ability to turn over its build volume multiple times in a 24-hour period lends itself to automated production. The post-pro DP will allow for automated depowdering, and then of course the post-pro SF100 will allow for vapor smoothing of these parts. If that's your intended desire for the finished goods of a vapor smooth part, you can certainly do it. One thing that's interesting is that vapor smoothing, in this case of TPC, when you get into fine strut diameters and things that need to flex and rebound, the actual vapor smoothing can actually help the durability of these parts by smoothing out any surface imperfections that could be the start of a surface crack or something that would lend itself to a failure. So the combination of printing with TPC, which is a highly durable material, and then the vapor smoothing process really refines it even further and gives you a product which has great durability, great longevity, incredibly smooth surface finish that feels good when it comes into contact with your skin in the area of prosthesis. It's a fantastic application. So just a couple of notes from our project we did. We did a super light midsole. This midsole only weighed 145 grams. If you would compare that to a resin-based midsole from Carbon, their midsole weight was 350 grams. So just from a competitive standpoint on what you can do with this material, it's amazing that we're less than half the weight of Carbon. That also translates to less than half the cost for production. And then there are much easier things on the finishing side, which aren't quite as obvious. For instance, you can use automated depowdering with our systems and recover all of that powder. I know with resin-based systems, people of you out there who've used resin-based systems, that middle step of where you have to clean the resin off of your parts is kind of painful at times, and it's wasteful, and it generates hazardous waste. But the key thing here is when you get into fine meshing, you're going to really raise the level of complexity in finishing, in cleaning out your part. Not so with powder-based parts. With automated cleaning, you can simply drop it in. It's going to clean all the powder out and allow you to recycle. For instance, if we were doing this this midsole with a resin-based solution, um, it really gets complicated in that you can't just simply dip the part in IPA. You basically would need a centrifuge to sling that thicker or higher viscosity material out of the part. So it becomes really complex when you start trying to clean intricate meshes with resin-based systems. And we don't have that with SLS. This is a huge advantage of powder based technologies. So again, just to highlight what we did in this project, we combined, 5 companies' efforts here to create an unprecedented number of shoes in such a short time. In 3 weeks' time, we were able to combine the design work from La La Land production to design for the midsole, The upper was 3D woven by a company in California called Variant 3D, which can quite quickly program a weaving machine to weave a 3D upper. And then partnering, of course, with Evonik for the TPC material and AMT for vapor smoothing. So it was great to see everybody kind of working on this project in conjunction and making it happen. And the first time through, I would say the success was quite good for such a condensed timeline to get everything ready and delivered to Formnext in just 3 weeks. So with that, I want to turn this over to Dwayne. Dwayne is a real footwear expert, and like myself, who don't really know much about shoes, but I've learned a lot from Dwayne and the guys at La La Land. And I can remember when I walked into their building and showed them TPC, there was a lot of buzz and excitement right away. And they've done some amazing things. They continue to innovate with TPC. So let me turn it over to Dwayne, who can give you some words from the expert view of how to use this material in footwear.
Hi, everyone. Just to give a little bit of background about our company, La La Land, we've been in the business of footwear and leather goods manufacturing the last 20 years. And pretty much we have been the only prime manufacturer for footwear in the country. And with recent, discussion of just onshoring manufacturing beyond footwear industry in general, there's been a very prohibitive element as far as just doing the manufacturing in the United States. And the largest part is obviously the skill issues and the high labor costs. And in short, I think printing technology like with Nexa, especially using TPC, really eliminates many of those problems. So just to get into the specifics of footwear, footwear business is said to be one of the hardest business to get into in the fashion industry. And mainly the most biggest reason or the biggest inhibitor is the components. And that is the soles, midsoles of the shoes. And traditionally, midsoles for the shoes are made with either EVA or PU. And the first, obviously, the biggest hurdle for that is the time part. So to open up a mold from the design, it usually takes somewhere from 18 weeks to 24 weeks. And that just to get one sample mold. So let's say, you got this sample and you have some changes to make, which usually happens, that takes you another 2-3 months to open another sample mold. And let alone the time, the cost is very prohibitive. If you were to get let's say, from US size 7 all the way to size 12 full size run of the molds, that's gonna cost you around anywhere from 29K all the way to 55K, assuming each mold costs 2,500s all the way up to up north of $5,000. And the last thing is, since these molds are very expensive, it comes with a very high MOQ. Obviously, you're investing this much just in the mold. So to get the money back from the business point of view, you're going to have to make, at least 1,000 or 2,000 pairs to really make it viable as a business. And as far as the process goes, these are 8 steps process that takes place over 24 weeks. So let's say you have a great idea and then, you have design and everything ready and you want to get your products out in the market. It's very unrealistic to do this anything under 6 months, let's say. So for that reason, footwear business in general is very high cost and just prohibitive for anyone that's new to join in. And that's one of the reasons that's stopping many people from, going into manufacturing and starting a shoe brands. Next slide, please. So with the Nexa 3D printer, the biggest, obviously, benefit is the printing speed, even compared to other printing technology. So we had a chance to have clients who work with carbon the carbon resin printer, and then also the HP MJF. And just from the production speed point of view, it's not a viable option. It takes very long time, especially this resin midsole we tried printing. This one took 26 hours to print just this. With Nexa, same design, it was less than a few hours. And second biggest benefit is obviously there's no tooling cost since it requires no mold. You only pay for the printing. So let's say, you know, you have 5 different concepts to try out. Instead of having to just, you know, narrowing down to one concept, you can make 5 different concepts at the same time. And the last thing is being able to produce on demand. So just in line with not having to make the molds, but this is very important now that the market has become more and more unique and the demand has been more catered towards customized solutions. The thing about feet in general is that every feet are shaped different. And if you look at the traditional way of last making and footwear making, the way that these people make these things called shoe lasts, it hasn't been really changed last, I'll say like 6-7 decades. So right now, the truth is in market, many people wearing shoes that's not supposed to fit on their feet. And even from the process point of view, so the whole process, let's take this project we worked on with Nexa, for example, from design all the way to manufacturing, it took less than 4 weeks, which is, you know, in traditional footwear industry, that's impossible. Next slide, please. So just to go a little bit deeper into the specific advantage that we oversaw with TPC is the ability to produce multiple concepts at once. And you might say that that's possible with different 3D printers, but really Nexa's advantage that we saw was the speed. Again, this also took almost like less than 3 hours to print. So when we initially had, within that 3 weeks, we were able to do like, you know, as you see in the slide, 5 different concepts. Whereas with the injection molding, that's going to take 5 separate molds and 5 separate costs just to get those samples. Next slide, please. And another great thing about TPC is the ability to control the performance. So if you look at any traditional compound like EVA or PU, in terms of performance, it's very static, and there's so much you can do to manipulate how it behaves. And if you look at any of, you know, let's say if you have any runner shoes in your closet, and if you wore them more than, let's say 6 months or let's say 1 year, you see them decompress, completely deform, you know, from the original form. So these traditional compounds doesn't even retain the performance so well. But with TPC, what's possible is you can manipulate the lattice structure to fit for a specific purpose. So let's say I'm designing a helmet for cycling. I can design a specific lattice to be shock resistance, or in this case of missiles, it's very important to have the bounce element to give comfortable support and cushioning. And by creating different size of lattice, even though it's the same design, all of them bounce differently. Energy return is different. So really detailed on how you design this lattice structure and make components that was purely impossible before. Traditionally, this was done through a combination of different materials. So for example, in the case of shock resistance, you know, it would be a combination of maybe EVA with extra TPU components or carbon fiber components, which has more cost and more time to execute. And not even print the whole also, but imagine like airbags from Nike. We can create a lattice that behaves airbag, so it becomes part of the component of an axle. So there's so many avenues you can take to make this material very performance focused in a way that wasn't possible before. Next slide, please. And again, I emphasize the speed of the Nexa. So one thing that was prohibiting us from getting into 3D is the fact that we could not mass produce with other machines. We don't do just concept and R&D in this company. We manufacture the footwear. And I think that's where you see so many cool concepts on Instagram, on internet, designers making some 3D prototypes, but you never see them going to market because it's purely not mass producible. But with Nexus TPC and the QLC printing speed, we were able to, or based on the spec, what we're told is we can make 10 pairs of this every day, which is incredible. Again, this with resin took 26 hours, and let alone just the cleaning process and everything. This one didn't even finish all the way. So I had to do kind of like a Mickey Mouse repair where, you know, I slice this off and just print the toe, connect them. So with resin printer, there's so many chances of failure, and let alone just the cleaning process, it's a nightmare. So going back to just bringing back the manufacturing to the United States, the benefit of additive manufacturing is eliminating the labor, high cost in the parts that's not necessary. But unfortunately, with resin printing, because there's so many cleaning process that's involved, it becomes labor intensive. So kind of diminishes the whole benefit of additive manufacturing. And the last thing I want to talk about is how you can dye these soles. So we had a client with who were using carbon printer and also the HP MJF. They're limited to specific colors that either the resin provide, or in the case of MJF, you're stuck to this very dark gray color. So let's say you have a great design with specific color schemes, you cannot make that to fit your design. You almost have to design the shoes after effect based on limitation. With this one, you can not only get solid colors, but as John showed us, you can do gradation, control the intensity of the color. So even from aesthetic point of view, the possibility is limitless, I would say. And that's my portion. Oh, actually, there's one more slide, sorry. And this is really exciting. So we recently got a biometric feet scanner to cater to specific demographic of clients, mainly the athletes who go through intensive training and really need customized footwear for their specific feet, you know, characteristic and purpose. Combined with TPC's elastometric physical property and the ability to control the performance through lattice, we can create a bespoke performance footwear, which was not possible before without investing so much money and time upfront. So as a conclusion, we're very excited as far as where TPC and combined with the footwear industry, where this is heading. And there are many things that wasn't possible with other printers. So from our end, we're very excited to just keep pushing these concepts and hopefully show a very interesting concept shoes in the market next year.
Yeah, great. Thank you, Dwayne. I think one of the things I wanted to highlight is, you know, the differences here between TPC and TPUs or TPAs or TPEs you see in the market is this material has 400% better toughness than those materials, which, you know, that's where you're going to really find a crucial performance advantage when you start meshing, when you need to flex. If the material just can't handle that, it's not going to work. So this is what we see time and time again of people that use TPU for SLS printing. It's not robust. It's okay to do a couple of parts, but it's not a production ready material because it just lacks that mechanical toughness and durability. So with that, let's yeah, go ahead, Dwayne.
Just adding to that, we actually had a client who printed, I think, 1,000 insoles with the TPU material. Unfortunately, they were all discarded because they didn't test it until the production. We bent it a little bit and it just rips apart. So
yeah. I mean, that's huge leap forward in the capability of all types of elastomers is to have an elastomer with such great durability. You know, one of the things I would point to in the orthotic and prosthetic industry is with this material, you can make things that are down to 1 millimeter or even under 1 millimeter thickness that have incredible tear strength and incredible mechanical toughness. And you just wouldn't find that with TPUs, in their tear strength and their durability. It just isn't there. So with that, I want to thank you, Dwayne. We'll also open this up for questions. Hopefully we have a lot of good questions out there for people that want to learn about this new material.
Yeah, absolutely. So you guys kind of covered this, but we had a question come in and I want to make sure we address this thoroughly, which is, how does this TPC material really differ from other elastomers that you might see in other 3D printing processes, right? We've done a lot of comparisons with TPUs with SLS, but what about TPUs and TPEs in resin printing, or TPUs and TPEs within FFF processes? And just kind of, we'll start with you, John, and get some feedback on that kind of from a macro view. And Dwayne, feel free to jump in if you have any specific experience as well.
Yeah, it really, with resin printing, I think we did cover this. When you get into fine meshing, it really complicates the cost of production on the post-processing side. Whenever you have to put a part in a centrifuge to clean it, you are obviously going to add an additional piece of equipment, an additional step, and you're going to be creating a hazardous waste byproduct with alcohol, which is saturated with the resin product, and you'll have to deal with that in some way or shape. So those are some key things. I think at the 30,000 foot, it's really about mechanical toughness and durability. This material is game changing for a material to be so soft, yet have such incredible mechanical toughness.
Absolutely, and super important for end user production components. And Dwayne, how about you? Do you have any specific experience with this material versus some of the other technologies?
Yes. So again, this sole that was printed with the resin, it's kind of similar to Carbon's EPU in terms of the property. It's almost too soft, So we definitely want, when we make the soles, to bounce, but we need enough structure for it to be sturdy when you're standing on. When you stand on this right now, the whole thing just compresses without enough ability to return the energy. With TPC, when I stand on this, nothing just compresses, but only when I'm walking in the specific areas that I'm giving pressure, it gives a return. So I've tried, just tons of different materials. It's just nothing like anything that I've seen before.
That's great. And what about you both talked about post-processing. How about the costs of production with a material like TPC versus some of these other technologies?
Yeah, I mean, that's a great point, Lewis. We're going to have big advantages just because we're powder-based and we're not going to have support structures or liquid chemical waste to deal with. We're going to be able to recycle this powder. The other big benefit here is the lack of support structures is huge. This material is actually priced less in the market right now than TPUs that you will find from other vendors like BASF. It's going to be much more durable, much more capable. So you've got two things. One is the initial cost of material. Second, if the material is 400% tougher, you're going to be able to consume less of it on a part-by-part basis. So it's really an exponential savings as your mechanical toughness increases. And then you're also on a powder bed platform, you've got savings coming from recycling and from less usage.
Which I think that's important to emphasize, because again, as you're looking at production, it can't just make technical sense, it has to make business sense. And I think that's
right.
kind of the big differentiator for me as well, as I was looking at this material. Okay. And then, we've got a flood of questions coming in now. First is, and this is an easy one to answer, is TPC commercially available already?
It absolutely is available. You can reach out to myself or Lewis or anyone at Nexa, and we can get you pricing on TPC and get it delivered.
And then a specific question, is this compatible with the QLS 230?
We are working on certifying it for the 230 right now. We do expect that to be completed rather soon. And we have already had some customers out in the field run this on the 230. And they didn't bother to give me a call and say they needed help. So I can only assume they had great results. So yeah, absolutely. This material is going to be available across all of the Nexa QLS platforms.
Thank you. Okay, this is one perhaps for both you and Dwayne. We'll see. It says, you mentioned, Dwayne, that the insole was printed in about 3 hours. Was
Yes.
that for one pair? And if so, what would the time estimate be for a full build?
John, if I'm correct, it was one side, right?
That was right. So for the build volume, let me just give a little bit of specs here. On the QLS 820, our build volume is 350 by 350 by 400 millimeters. So depending on what size of shoe you're printing, and we have to remember that we could go all the way down to kid sizes, all the way up to a size 15, you could fit those parts in there with a spacing. And I see another question about spacing. We really only need to give a couple millimeters in between parts. So you can really stack and nest. And if you're doing a run of, say, shoes that range from a size 5 to a 15, then you could certainly mix and match those and nest the parts the most effectively. The beauty of the QLS is running this material. We have the possibility of turning over the build a minimum of 2 times per day, potentially even 3 times per day. So whatever you can nest in that build of 350 by 350 by 400, we can turn that build over twice a day at minimum. So you can do a lot of production on one machine. And I do see a question about the cost of the machinery. Our QLS 230, which we still have some available this year, are starting at $70K. For that size of build envelope, depending on the footwear size you want to build, you're going to have to angle it a little bit, but you can certainly do a range of parts in that machine at 70,000. Our QLS 820 starts at 500K.
Awesome. Thanks, John. And then
I see a question. This might help you, Dwayne, or be something you can help with, Dwayne. What kind of adhesives can you use to bond it to the soles with TPC?
So if I'm correct, we use the regular the what is it, permanent cement for soling that's UV cured. I don't know the specific chemical compound of it. I can find out, but we didn't use any other special glue. It's the same one we use for EBA sole or PU sole. It's UV cured, so it's permanent.
And so I see another question about long-term fatigue test from David. David, thank you for visiting us at FormNext. I'll say that because I remember having a good conversation with you there. We don't have long-term fatigue test results. However, it should be noted that in comparison to EVA, I believe the cursory results so far, I think it show it's going to be better than EVA for this application. But this is a new material, so we look forward to continuing to work on those long-term tests, David. Thank you. Next question, what are QLS doing to compensate for packing compression of the powder while printing to get consistency and proper density? So that's one I would have to refer over to the engineers who developed the machine. They do an excellent job. We do use a roller, a counter-rotating roller in the 820, and we're able to print a density of build anywhere from 5 to 20%, depending on the geometry we can pack in there.
Great. Okay. And then it looks like we are coming to the end of our questions. So I have 2 more, one for each of you. First with John. John, we've talked a lot about footwear today, but what do you think about the possibility of potential of TPC for other applications requiring elastomeric performance in a production environment?
Yeah, it's actually amazing, Lewis. I mean, it's no surprise that we started this TPC endeavor with footwear because it's something everyone can relate to. However, this material is awesome for automotive, where you need flexible ductwork, things that are very complicated to manufacture and take a lot of tooling costs. Certainly TPC is amazing for that. It has good heat deflection, very, very strong chemical resistance. It's a very, very durable material. So the applications in ducting, in automotive, in soft touch componentry is amazing. I think one of the big things that we're just starting to scratch the surface on 3D printing is how softer materials can impact robotics, specifically robotic hands and things like this. If you think about all the products in the market that have been designed around the softness of a human hand and its ability to touch and grab, a metal robotic hand isn't really ideal. So thinking about how to use TPC for flexible robotic grippers and soft touch applications, I think it's just an unlimited capability there to do that. Even into, obviously sporting goods, helmets, protection, all types of customized protective personal protection equipment, maybe even into firefighting gear, bicycling, motorcycle, any sportswear you can think of, I think could be helped by the addition of TPC.
Thanks, John. And before we go over to Dwayne, we do have one more technical question roll in. Does TPC have any issues with static cleaning? In other words, does it stick to the roller or other parts of the machine?
No, we don't see that. The printer prints with it very, very well, unlike what you would see with PA11, where it sticks to everything and becomes kind of a maintenance challenge for any 3D printer. I think TPC is a great solution for companies who may be struggling with that side of PA11 in terms of printing orthotics or materials that need to be flexible. The great thing about this material is what we've shown you today are very, very thin geometries that flex the way we want. When you thicken this material up, it has some softness to it at Shore 95, but it is very, very tough. When you thicken it up, it becomes incredibly strong. So I think it's a perfect material for doing footwear orthotics. And I think that hasn't really been in the market long enough to address that, but we're working on that now with some prosthetic and orthotic companies as we speak. And I think it's going to be a game changer for that market.
Totally agree, John. And Dwayne, my last question, for you before we close up for today is, you are kind of at this unique position. It's a convergence of creativity, utility, a little bit of engineering. When you think about TPC and kind of the future of what you could do with TPC at La La Land, what are you most excited about?
I think it's so from us manufacturers' point of view too. Let's say when we want to try new concepts, let's say we have a new shoe we want to design, we have to go through the same process as our customer where we have to open the mold and everything. Just the thought of going through that, we weren't able to even start on those fun ideas and concepts. And just the thing about shoes in general, this is something that I think personally is it hasn't changed for as long as we can remember. I think last 100 years, the way it's been made. And shoes are something that everyone wears. And I'm just curious why there hasn't been enough innovation in that field, right? And from design point of view, I think because it's an extension of fashion, I think it's been dominated by fashion design. But I think now that, even the country is shifting toward more of additive manufacturing rather than labor-based manufacturing, the whole industry is shifting towards more of an industrial design route. And with that, I think there's just going to be a possibility that we couldn't even thought of like before. I think if you look at last few decades, one of the greatest inventions were done by guys like Nike. To take an example, like a air pocket that you see in the Air Max. You can do something like that with lattice, but since you're not limited to one property, like I said, it can be shock resistance, it can be for energy return, it can be for energy absorption. I think there's just going to be so many new products and concept that you have never seen before or you thought was impossible. So we're just excited, to be honest, not just footwear because we do bags and different accessories, but just to kind of be able to have an idea and just be able to execute.
Awesome. Thank you, Dwayne. I think that's a wonderful high note to end on. If you have any more questions about TPC or for John, the team at Nexel, or even Dwayne, feel free to email us. You'll get a follow-up email after this webinar where we'll share the on-demand recording with you guys. You can forward that to colleagues and friends as well if you'd like. And you can also respond to that with any questions you may have. If we did not get to any questions from your team today, we'll be sure to reach out individually. I know we had some rather technical machine-based questions, so we'll be sure to get to those as well. But thank you all so much for your time. Thank you, John. Thank you, Dwayne, for joining us today and for presenting. And we look forward to the future of TPC.